Hello everyone, I'm Karthik Raman and I'm a HPC Solutions Architect at Amazon Web Services. Today I'll be joined by Dragos from NVIDIA and we are going to talk about interactive scientific visualization on AWS with NVIDIA Index. Our agenda would be as follows. I will first talk about some of the common challenges users face with scientific visualization today. Then I will cover briefly on the HPC infrastructure and services on AWS. Dragos will then talk about the NVIDIA Index technology for scalable visualization. Then I will cover the index architecture and deployment solution on AWS. We will then show a demo of index running on AWS and close with a summary and call to action. So scientific visualization is critical to understand complex phenomena modeled using HPC simulations. However, it has been challenging to do this effectively due to the inability to visualize, explore, and analyze very large volumes of data and lack of collaborative workflow solutions. Standard visualization workflows are characterized by sequential, time-intensive set of steps which include running simulation for days, weeks, or even months, and then preparing subset of output data for visualization, transferring and loading the data into visualization software for analysis, sharing the findings, and then repeating the process with another subset of data and running additional simulations with new inputs. So such a workflow is not very practical in an on-prem environment due to compute and storage resource constraints, and then collaboration challenges, and above all, the time wasted if the visualization data demonstrates that the simulation data itself was invalid. So NVIDIA Index on AWS addresses each of these problems by providing a collaborative and scalable scientific visualization solution. But before diving into the details of index technology and its architecture on AWS, I would like to briefly talk about HPC on AWS. So why run your high performance computing workloads on AWS? So at AWS, you have access to virtually unlimited infrastructure. This allows you to scale on demand very quickly, and you will only pay for what you use. For an on-prem installation, you are generally limited to the fixed size of your cluster. If you need to go from, say, 100 instances to thousands of instances in minutes, AWS enables this elasticity. By eliminating job queue times and scaling your cluster as high as needed and when you need it, you can reduce the time to market or, say, a publication. Also, the agility of AWS allows you to fail fast and iterate quickly, and this reduces time to results. AWS now spans 77 availability zones within 24 geographic regions around the world. And with this global footprint, you can increase collaboration with access to clusters from around the world. From weather modeling, reservoir simulations, and to genome mapping, HPC has always been about solving the world's most complex problems. The AWS HPC solution combines the latest compute, networking, storage, security, cloud orchestration, and visualization technologies, and it provides users a highly customizable computing platform with a strong partner and ISV community. The AWS HPC solution allows you to choose from a variety of compute instance types that can be configured to suit your application needs, including CPU, GPU, and FPGA powered instances. By moving your HPC workloads to AWS, you can get instant access to the infrastructure capacity you need to run your HPC applications. At a high level, these are the list of services that customers use to run their HPC workloads on AWS, starting with data management and data transfer. So there are multiple ways to get your petabyte scale data from your on-prem infrastructure to AWS. Services such as AWS Data Sync, Snowball, Snowmobile, Storage Gateway, and Direct Connect allows you to transfer large amounts of data to S3. For compute, AWS offers more than 270 different types of instances, including the latest generation of CPU and GPU instances. When it comes to network, AWS provides a network interface for Amazon EC2 called as EFA, which is also known as the Elastic Fabric Adapter, which has a unique OS bypass networking mechanism that provides a low latency, high network bandwidth of up to 100 gigabits per second for inter-instance communications. When it comes to storage, AWS offers services like EBS, which is the Elastic Block Storage, EFS, which is the Elastic File System, and S3, which is the Object Storage. And then there is FSx for Lustre, which is a fully managed high-performance Lustre file system. When it comes to orchestration, services include AWS Batch, AWS ParallelCluster, and Engine Frame. And when it comes to visualization, we offer services like NiceGCB and AppStream, which provides customers a remote visualization solution for post-processing and data analysis. And then you have services like Amazon Cloud Watch, which is a monitoring service for AWS cloud resources and the applications you run on AWS. AWS IAM, also known as the Identity and Access Management, enables you to manage access to all these AWS services and resources securely. And then you can use AWS budgets for cost tracking. So now I'm going to dive a bit more deeper into some of the HPC services mentioned earlier, which are also used for the index solution on AWS. I'm going to start with the Amazon EC2 GPU instances. So there are 4 types of GPU instances that AWS offers. The P3 instances are ideal for parallel compute intensive tasks, especially in the areas of machine learning and high performance computing. P3 offers up to 8 Nvidia V100 Tensor Core GPUs, and each GPU has up to 32 GB of high bandwidth memory, and these instances offer up to 100 gigabits per second of networking throughput, and it supports NVLink for GPU peer-to-peer communication. The G4 instances are used for graphic intensive applications like remote graphics workstation, video transcoding, and game streaming, and also used today in production for many machine learning inference applications. So G4 offers up to 8 NVIDIA T4 Tensor Core GPUs with 16 gigabyte of memory each and up to 100 gigabits per second of networking throughput. We also offer the P2 and G3 instances, which are the earlier generation of NVIDIA GPUs. The Amazon EC2 instance based on NVIDIA Ampere, which is the A100 Tensor Core GPUs, will be offered soon. I would highly recommend you to sign up on AWS page for updates and availability. Now let's dive a bit deeper into the different available storage options. So beyond instant storage, there are 3 different high performance storage options. First is EBS, also known as Elastic Block Storage, which is our primary solution for durable high performance storage for your EC2 compute instances. With EBS, you have the flexibility to adjust your volume, both size and performance on the fly with no disruption to your workload, and you can also take point-in-time snapshot to back up your EBS data. Next is EFS, which is the Elastic File System. It is a fully managed network file system. It can grow and shrink automatically as you add or remove files, so you do not need to provision and manage capacity to accommodate growth. Then we have the Amazon S3, which is the object storage service. S3 offers a highly durable, highly available, and scalable data storage infrastructure at low costs. It stores data as objects within buckets. You can control access to individual buckets and objects within the bucket. So for high performance computing, parallel file system is very important. Amazon FSx for Lustre provides a fully managed Lustre file system that allows file-based applications to access hundreds of gigabytes per second of I/O bandwidth, millions of IOPS, and sub-millisecond latencies. The Lustre file system provides a POSIX compliant file system interface and can scale to thousands of clients. It's a fully managed version of the Lustre parallel file system. It provides consistent sub-millisecond latencies due to the parallel file system design, with clients talking directly to servers and also the SSD-backed storage. For visualization, AWS offers NiceGCB, which is a remote desktop cloud visualization service. So NiceGCB delivers high-performance remote desktop and application streaming. With NiceGCB and Amazon EC2, you can run graphics-intensive application remotely on EC2 instances, and stream the results to a simpler client machine, thus eliminating the need for expensive dedicated workstations. Customers across a broad range of HPC workloads use NiceDCV for their remote visualization requirements. And there is no additional charge to use NiceDCV on Amazon EC2. And NiceDCV supports both Windows and Linux operating system. So the NiceDCV streaming protocol is actually also used by Amazon AppStream, which is a fully managed desktop streaming service. For HPC orchestration, one of the key services we have is AWS ParallelCluster. So AWS ParallelCluster is an AWS-supported open-source cluster orchestration service. It simplifies deployment of HPC cluster in AWS as it easily integrates with other key HPC AWS services like Amazon S3, Amazon FSx for Lustre, the Amazon EC2 instances so that you can specify the type of instance you need, then enable EFA on supported instances, enable DCV for remote visualization, and it also supports schedulers like Slurm and AWS Batch. As a user, you deploy a cluster by specifying your resource requirements in a simple configuration file. So this is a short video snippet on how AWS ParallelCluster works. As a user, you can iteratively decide on the best CPU, GPU, memory, or I/O architecture for your workload. You can test multiple options in parallel rather than sequentially and dispose of what you don't need. You can make CI/CD as part of your HPC practice. These are a few notable customer success examples utilizing AWS HPC services and solutions in the area of drug discovery and research. Celgene, now part of Bristol Myers Squibb, have been able to utilize AWS HPC infrastructure and services to speed their R&D experimentation, allowing them to get results in hours instead of weeks. Fred Hutch, which is a cancer research center, have been running their genomics workflow for microbiome research on AWS to process more than 15,000 biological samples, thus reducing 7 years of compute time to 7 days. And this has really helped their researchers to get their results very fast. Also, another notable use case in the oil and gas space is with Shell in the area of machine learning. So geoscientists commonly spend up to 70% of their time finding and collating data. And these exploration workflows are extremely manual and labor intensive, and it requires months to generate high quality interpretations. So Shell partnered with AWS to develop a data platform which helped drive these subsurface innovations and enable machine learning to transform upstream workflows. Shell has already successfully migrated their subsurface deep learning research program to the AWS platform, and they have achieved a 3x performance improvement on their machine learning applications. With that, I would like to call upon Dragos from NVIDIA, who will talk about the Nvidia Index Sdk.
Thank you, Kartik. Let's now talk about NVIDIA Index. NVIDIA Index is a 3D volumetric interactive visualization SDK that allows scientists and researchers to visualize and interact with massive datasets, make real-time modifications, and navigate to the most interesting parts of the data to gather better insights faster. And all in real time. Index is horizontally scalable and elastic. You can easily add and remove nodes at runtime as you load more data. Its versatility comes from the ease of deployment and the clientless approach. The user can just connect with the browser to the HTML5 viewer. Index leverages GPU clusters for scalable real-time visualization and computing of multi-valued volumetric data together with embedded geometry data. Let's have a look at the workflow. At first, the input seismic data is split into smaller cubes called subregions, which get assigned to different nodes and GPUs. Then each node will import only its assigned subregions. Now that the data is on the GPUs, rendering can start. Each node will render its subregion and everything will be composed together at the end. Now let's imagine that we want to add more data. We can just increase the extent of the volume, And to keep the interactivity, new nodes can be added to the rendering process. Index will dynamically redistribute the subregions accordingly without needing to restart. Scientists, researchers, and engineers use Index in diverse domains such as microscopy, healthcare, medical, or astrophysics. Sometimes to visualize galactic winds to help understand the evolution of the universe. And sometimes to visualize the velocity field around the lander as it hurtles towards the Martian surface to help bring people to Mars. And sometimes to visualize the nanoscale structures of cells to help study the behavior of viruses such as the SARS-CoV-2 virus. Researchers can visualize expansion microscopy and lattice light sheet microscopy to derive knowledge from large data in real time. Index is also used in production in the oil and gas domain. Its primitives map very well to this domain, with seismic volumes, height field slices, triangle meshes, wells, and reservoir grids. There is always the possibility of accessing and editing volume through its compute interfaces, which is quite useful to carve out meaningful information from the raw data. Index is integrated in ParaView as well, one of the most popular visualization tools in HPC. That means that users have access to index features by default with the latest ParaView version, so they can experience real-time interactivity with their existing volume visualization workflows. One of the most interesting features that NVIDIA Index has to offer is its Index Accelerated Computing Technology, or Xac. It allows for runtime customization of the volume rendering through a Xac Shader program, which is based on CUDA code. The Xac Shader runs on the GPU against every data voxel to compute the output color for that voxel. On the left, we have the plain rendering of a seismic volume. On the right, we have the same volume with the Xac Shader applied. Notice all the extra cues between the rock layers. With Xac Compute Program, it's also possible to edit the voxel data itself, not just read it. You can run inferencing on the GPU, whose output can be passed to an Xac Shader compute program evaluation. It's also possible to query data points in the volume along array. Index is very well suited for in-situ and in-transit visualization. With data locality, it's easy to manage the collocation of rendering and compute. It's also easy to launch jobs that fetch data from different compute or simulation clusters. At its core, NVIDIA Index is a visualization library, but around it are many building blocks that provide a lot of additional value. These building blocks are weaved together in the viewer application. So what is the application? It's an HTML5-based viewer which has a server that implements, at the most basic level, rendering, video stream distribution to the client, and control through the web API. Each rendered frame is H.264 encoded using NVENC and sent to the client side through a WebSocket. The client, a React-based HTML application, reads these frames and pushes them to a media source extension for decoding by the browser. For user actions like color map editing or camera rotation, even Xac program editing, there is a JSON RPC web API that happens over a WebSocket channel. Each client session gets its own pair of WebSockets, one for video and one for command. But it's also possible to run the NVIDIA application as a rendering service. That is, embed the video stream in your own application and use the web API for commands. In this example, we can see a Jupyter Notebook connecting to the Index application server. Furthermore, you can have additional web API commands in your extension. Which brings us to the next slide. About the architecture. The server is made up of components that are split by functionality. Data importers are used for loading data from different formats. The scene management component provides an API for working with the scene. The Web API component is responsible for registering and dispatching Web API commands to the relevant components. The video streaming component is responsible for managing the video stream for client connections. The application itself uses these components to implement the viewer. But one can also implement a different application reusing these components. And the user can also add their own components. Like in this slide, we see the viewer gain the possibility of loading VDS data, which is the new industry standard format, data format for oil and gas, through an open VDS plugin. We also added an extension that allows importers to read data directly from S3 buckets. Instead of copying data from S3 buckets to a local file system, now it's possible to read the data directly from the bucket. It's a very convenient and cost-effective cloud solution to data management. These two extensions were developed in collaboration with AWS. But you can imagine building your own extensions, like implementing AI inferencing or implementing in situ visualization, like fetching data from a compute cluster, or creating a Web API component that implements commands that your application can call, or the other way around, call your application from within a plugin. And from here, I give it back to Kartik to present how Index will run on AWS.
Thank you, Dragos. Now I'm going to talk about the Index architecture and its deployment solution on AWS. So you have two options for 3D volume rendering using Index on AWS. That is either using a single instance for relatively smaller datasets or using a cluster of instances for larger datasets. This is the high-level architecture for single instance rendering. In the case of single instance rendering, you will deploy an Ec2 GPU-based instance in an AWS region using the Index AMI from the AWS Marketplace. An AMI, or Amazon Machine Image, is a template that contains the software configuration, for example, the operating system, the application, and its dependencies. And all the infrastructure is deployed using AWS Cloud Formation. So AWS Cloud Formation is a text-based file written either in JSON or YAML format that describes all the AWS resources you need to deploy to run your application. The set of AWS resources are created as a stack and is managed as a single unit when AWS Cloud Formation instantiates a template. The custom datasets that are required for volume rendering should be uploaded to Amazon S3, which is the object storage service. With the Index S3 plugin, you can directly render your data from S3 without copying them to local storage. Optionally, the EC2 instance can be backed by an EBS volume if needed. For example, if you want to render using visualization software like ParaView. When the Ec2 GPU instance is running, you either enable port forwarding via SSH tunneling to the instance or enable the port 8080 in the Ec2 security groups. Once the connection is established, you can log into the Ec2 GPU instance and execute the Index viewer script along with the sample or custom dataset for visualization. So in this case, we use Index's HTML5-based client viewer that receives a video stream from the Index server running on EC2 and allows for socket-based transfer of user interactions or commands back to the server to steer visualization. You can use a browser on your client system to render and visualize your output. You can use a single instance with single or multi-GPUs. Index will automatically scale to the maximum number of GPUs on a given instance. In the case of cluster rendering, you will launch a cluster of Ec2 GPU instances using AWS ParallelCluster, which is the cluster orchestration service I mentioned earlier. You will launch a cluster with the required resources, for example, the type of GPU instance, the Index Amazon Machine Image ID that you obtain from AWS Marketplace, specify the storage requirements, for example, the S3 bucket access and or enable EBS block storage, the type of scheduler, in this case Slurm, and also enable remote visualization using nice TCP. All these requirements are specified in the Parallel Cluster configuration file. Once the cluster is created and running, users can log into the head node using the nice TCP client or web browser and launch the index Slurm script along with the sample or custom dataset for visualization. The index Slurm script is just a wrapper that adds required parameters for network configuration based on the environment variables set by Slurm Workload Manager for your cluster. Once the job is running and the server IP of the viewer node is printed on the terminal, you can open a browser in the nice TCP session and start visualizing your data. With the auto-scaling feature, you can start with 0 compute nodes and only scale up when your job is launched and automatically scale down when the job is terminated. We have also added a capability in the index Slurm job script which allows you to scale up or down in an existing running rendering job. Now we will show a demo of Index running on AWS. So in this demo, we will create a GPU cluster and all the other required resources using AWS ParallelCluster. We will render a sample dataset using Index. We will show how the auto-scaling feature works and how to scale up a running Index job. We will also show how you can use Index as a service using Jupyter Notebook. So let's begin. All right, so we will start by creating a GPU cluster using AWS ParallelCluster. So AWS ParallelCluster is distributed as a Python package and can be installed using pip. So you just open a terminal and say pip install AWS ParallelCluster. In this case, we specify a particular version because the Index Amazon machine image that we are using is tied to this particular version of ParallelCluster. Okay, so once you install ParallelCluster, you can just type pcluster version to confirm the version that you just installed. And then you will have to create a ParallelCluster configuration file. So the ParallelCluster configuration file, if you recollect, is just a simple text file and it specifies all the key resources that you need for your cluster. So at the top, we have the AWS section, which specifies the region name. And here we are creating our cluster in US West 2 region. Then in the cluster section, you specify all the key resources needed. For example, the type of instance for your master node, the type of instance for your compute node, the type of scheduler that you need. We will be using Slurm. The initial queue size and the max queue size. So the initial queue size specifies the number of compute instances that you need when your cluster is launched initially. And the max queue size specifies the maximum number of instances that you can scale up to. Then the S3 bucket access, where you've stored your data. Then the custom AMI field specifies the index Amazon machine image ID that you get from the AWS marketplace. Then you also enable DCV by default for your master node so that you can log into the master node using a remote desktop. So we have actually provided a sample ParallelCluster configuration file in the GitHub repo. So you can use the same and just modify the necessary fields per your requirement. So once you create the configuration file, you can just type pcluster create and you specify the cluster name that you want to create. It can be anything. I'm just going to type, I'm just going to say index cluster demo. And then you specify the cluster configuration file that you just created with the -c flag. All right, so when you type the pcluster create, what's happening in the background is that AWS ParallelCluster is actually creating cloud formation templates, which are all the resources that you need. So if you remember the cloud formation, I have mentioned about cloud formation briefly. So these are just stacks of resources that are created on your behalf by ParallelCluster so that you don't have to worry about creating those templates. So once the cluster is created, you can just log in to the head node, do your work, submit your jobs, run your simulations. And once you're done, you can just exit and then delete the cluster. And ParallelCluster will automatically delete all the resources that are created on your behalf. Yeah, so ParallelCluster manages everything, so you don't have to worry about creating those resources manually. So we're just going to wait for the cluster to create. Okay, now that our cluster is created, let's log into the head node. You can do that by simply typing pcluster ssh and the name of the cluster. So that'll be index cluster demo. Since we have used the Slurm scheduler, you can type the basic Slurm commands like sq, sinfo. As you can see, you have two compute instances available since you mentioned the initial queue size as 2 in your parallel cluster configuration file. Let's log in to one of the compute nodes. So this is the P3 8x large instance. And when you type NVIDIA SMI, you see that there are 4 V100 GPUs on this P3 8x large instance. But for our demo, we will be running the index Slurm job from the NiceDCV remote desktop session. To do so, we will just log out of the cluster and type pcluster dcv connect index cluster demo. That is the name of the cluster. And you will log in to the remote desktop session on the head node from your browser. Just accept some default settings here. And you're ready to go. All right, so now I will hand it over to Dragos, who will show Index live in action.
Thank you, Kardik. Let's see now how to start NVIDIA Index. So let's open a terminal. Go to the package directory. Before we start, I would like to mention that the AMI contains sample scenes from various domains, like astrophysics, geoscience, microscopy, and medical. We're going to use the brain dataset, which is a scan of a human brain at nearly cellular resolution. So to start, we do srun, because we're using Slurm to launch on the compute nodes, and vindex Slurm, which is our Slurm wrapper script, and vindex viewer, which is the main entry point script for launching the index viewer, and then the scene file. So you're seeing now index starting up on two nodes. One node will be the viewer node, and the other node will be a worker node. Of course, you can have more worker nodes attached. We will see this a bit later. Once started, Index will start importing data on all nodes in parallel. In this case, it's reading directly from S3 buckets. This is going to take a bit as we're loading 52 gigabytes of data. And it's done. So let's open it. And now we can examine the data set. So we can rotate the camera by moving the mouse. We can zoom in and out by pressing Shift and moving the mouse up and down, or panning by pressing Control. Okay. So let's look at the color maps. Manipulating the color map will enhance certain aspects of the data by tuning the color and opacity of certain data ranges. For example, let's tune this range of 0.1, 0.2 to make it more opaque. So we have opacity on the vertical scale, and you already notice the data features changing. Let's make it more transparent. Again, notice the changes. So let's bring it back to how it was. One way of roaming through the data is by changing the region of interest. So for example, now I'm changing the z-axis, so the region of interest in the z-axis, to roam through the data. This scene contains an Xac shader in action. So let's have a quick look at it. Let's open the program. So we have it right here. I'm not going to go through it. I just want to demonstrate that it's possible to change the program at runtime and recompile it. And we see the change happening. And now let's close this. Also, let me disable the program, and notice how without the Xac program the volume seems to have less visual features. Okay, now we're going to demonstrate how index can scale by adding more worker nodes. So we see here there are 2 worker nodes, and now I'm going to add one more. So we currently have only 2 nodes in the cluster, and we want to allocate more. So now additional instances will get spun up. And Kartik will provide more details about this.
Thank you, Dragosh. So the way the autoscaling works with Slurm is that when scaling up, there is a process called Job Watcher that runs on the head node. It determines the number of compute nodes that are needed to fulfill the computational requirements specified by the number of nodes and the slots per node in your Slurm job script. Similarly, while scaling down, there is another process called Node Watcher, which evaluates the idle time of the node. If there are no pending jobs in the cluster, and if the instance is idle for a period of time longer than the scale down idle time, then the compute nodes are terminated. The default value for the scale down idle time is 10 minutes, and you can control this in the Parallel Cluster configuration file.
Okay, it's done. So now you should have 2 more nodes. There they are. So now we have to fetch the original job ID of index. So this is 9. And run srun minus n2 because we want 2 more nodes, and vindex slurm, the wrapper script. And this is the special part, attach to job 9. And in the end, run the viewer without any parameters. Okay, now the workers are starting up on the nodes. So you can go back to the browser. Now the additional worker nodes are starting up, and then the data will get redistributed to all 4 nodes. This is going to take a bit. Okay, so now we have 4 nodes. Notice also the performance improvement. And now we can move on to the last part of the demo, which shows how to use the application server in a Jupyter Notebook. So I will launch the Jupyter Notebook now. This is the loaded notebook. And we have the viewer IP here, which is running on one of the compute nodes. And now we're just going to go through and connect to the viewer. Below we have some helper function to update the region of interest and read the region of interest. And let's use them to make a small animation. So here you have the data roaming in an animation. So let's look at color maps now. Again, we have 2 functions, one for reading and the other one for updating the color map. So let's do something really simple. Let's set the first half of the data range to the same red color with the previous opacity. So here it is, the same red color. And in the end, we can actually use a pre-existing predefined color map from matplotlib. So there's quite a list here, but this is set up for the Viridis color map. And here it is. It's updated. So as you can see, NVIDIA Index is quite a powerful tool that can be used either as a standalone viewer or as an application server that can be controlled.
Thank you, Dragosh. So today we would like to announce the availability of the NVIDIA Index AMI in the AWS Marketplace. So if you go to the AWS Marketplace website and search for NVIDIA Index, you should see the listing for the Index Amazon machine image. The listing also has the detailed architecture that we went over earlier in this talk, and it also has the links to the repository with step-by-step instructions on how to launch Index on AWS. So to conclude, scientific visualization impacts all research disciplines. It is hard to use traditional visualization solutions on massive datasets gathered by these complex simulations. NVIDIA Index on AWS addresses these challenges by providing a scalable and distributed GPU-based architecture for both highly parallelized high-performance computation and visualization. We would highly recommend you all to subscribe to the NVIDIA Index AMI on AWS Marketplace. And if you are getting started with HPC on AWS, would also recommend the AWS HPC workshops, which is a self-paced hands-on tutorial on the different AWS HPC services. With that, we would like to close and thank you all for joining our talk today.